Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 27th lecture. In this lecture, we will be discussing technology mapping. In the earlier lectures, we had seen that logic synthesis consists of various subtasks which are shown in this figure, and in earlier lectures, we had discussed RTL synthesis and logic optimization. So, at the end of logic optimization, we get a netlist which is in the form of generic logic gates, or which is netlist which is in terms of generic logic gates, and it is optimized. Now, after we have got a netlist which is optimized and in terms of generic logic gates, we need to carry out a task which is known as technology mapping. So, what does a technology mapping do? So, technology mapping basically transforms the netlist which is represented in terms of generic logic gates to a netlist which is in terms of standard cells which are in the technology libraries. So, in this lecture we will be looking at technology mapping. So, first let us look into the framework of technology mapping. So, the framework is shown in this figure. So, it takes these inputs and produces a mapped netlist which is the output. Now, what are these inputs? So, the first input is a set of technology libraries. So, for technology mapping, we need to provide to the logic synthesis tool the set of technology libraries from which the cells will be picked and will be used in the netlist. Now, just to recap, when we looked into technology libraries, we discussed that a technology library consists of various kinds of cells, right, and these cells perform different logic functions. For example, combinational logic functions like AND gate, OR gate, AND or invert and multiplexer and so on. And there can be sequential circuit elements also, such as latches and flip-flops. Additionally, for the same logic function, a technology library can contain cells of different sizes, right. So, for example, for a logic function of NOT gate or an inverter, we can have a inverter of size 1x, where x is some unit of area, or there can be an inverter of size 2x. Then there can be third inverter which has a size of 4x and so on. Similarly, for other kind of cells, for example, NAND gate, NOR gate, OR gate, AND gate, there will be multiple cells of different sizes which deliver the same functionality. Additionally, when we provide technology libraries to the logic synthesis tool, we can provide technology libraries of various types. So, what we mean by type is that there can be some technology library which is implemented using transistors of, say, low threshold voltage, right. So, low threshold voltage or low VT. So, the transistor in this case is a low VT, meaning that it works at lower threshold voltage and it turns on much easily. So, when a cell is implemented using transistors which are of low threshold voltage, then typically its speed is high, but it also consumes more power, right. And similarly, there can be another technology library which is in which the cells are implemented using transistors of high VT, right. So, it can have a high VT. So, for this the speed will be lower, right. Speed will be lower because these transistors require more voltage to turn on. So, the speed will be lower, but it will consume less power dissipation or consume less power, right. So, when we provide technology libraries to the technology mapper, we may provide a set of libraries, meaning that some library can be of low VT, some can be of high VT and so on. Now, and then another input or the most important input that we need to give to the technology mapper is the unmapped netlist, right. So, what is an unmapped netlist? So, this is a netlist which is implemented in terms of generic logic gates. So, just to recap, generic logic gates do not have a transistor level implementation. So, the function is well defined for generic logic gates, but its transistor level implementation is not defined, and therefore, the area, the timing and the power dissipation, these things cannot be estimated for cannot be computed for generic logic gates. So, when we give a design to a technology mapper, the design is in terms of netlist, and that netlist is implemented in terms of generic logic gates. And the third important input that we need to give to the technology mapper is the constraints, right. So, we have seen in the last lecture that we can represent constraints using SDC format, synopsis design constraints format, or these constraints are in the .sdc files, right. So, we can give the SDC files as input to the technology mapper, and using these so what information does the SDC files contain? So, SDC file contains information about the clock frequency, the environment of the design in which a design is expected to work and so on, and based on this constraints file, the mapper can take its decision that for which path, which kind of cells needs to be instantiated in the netlist and so on. And also the while performing optimization, a technology mapper needs to know that what is the objective, or what is the objective it is required to meet, right. For example, the objective can be, we want to minimize the area for our netlist under a given delay constraint, or it can be that that we want that the mapper should minimize the delay under a given area constraint. So, these are some examples of the objectives that the tool needs to or the mapper needs to consider, right. Now, in logic synthesis tool, there are options like effort high, effort low and so on, and based on these effort the effort level of the logic synthesis tool, the objective of the technology mapper can change, right. For example, if the effort is high for timing, then the primary objective of the technology mapper will be to minimize the delay, right. So, in addition, so given these all inputs, what does a mapper do? A mapper produces a netlist consisting of library cells, and while producing this netlist, the most important thing that the mapper should consider or ensure is that the unmapped netlist and the mapped netlist, these two netlists must be functionally equivalent, right. So, the functional equivalence must be preserved. So, what we mean by functional equivalence is that for a circuit, if we are giving a sequence of zeros and ones at the input, then it produces a sequence of zeros and ones at the output. So, these for the unmapped netlist and also for the mapped netlist, the sequences produced at the output should be exactly same for a given set of input sequences of zeros and ones. So, that is what we mean by functional equivalence. Now, let us take an example to understand that what is done in mapping. Let us consider this netlist, which is in terms of generic logic gates, meaning that G1 and G2 are generic logic gates. Since G1 and G2 are generic logic gates, the area, delay and power for this netlist cannot be computed, However, the functionality is very well defined, and we can represent this functionality as y is equal to a dot b, meaning that this is because of this AND gate, we have this signal as a dot b, and then we have a NOR gate. So, that is why we have a dot b plus c whole complement, right. So, the function for this net list is very well defined, but other measures, other PPA measures like area, delay and power, those are not known. And for this netlist, let us assume that a set of libraries is given in which these are the cells, right. Now, we are taking only a few cells just for the illustrative purposes. Typically, a technology library will contain say hundreds of cells, right. But let us, for the illustrative purpose, let us assume that the technology library contains only these 4 cells. So, we have an inverter, right. We have NAND gate which is written as NAND 1, and then is another NAND gate which is NAND 1 underscore LP, just to signify that it is implemented in say high threshold voltage transistors, and therefore, it will consume low power, and that is why we have underscore LP here, right. And then let us assume that there is another gate which is AND 1, right. Now, for these logic standard cells or cells in the libraries, the PPA measures are unknown, right. For example, the area, the delay and power numbers, these things will be specified in the technology library. So, in the format that we have discussed earlier, right. So, let us assume that these numbers are given, for example, for inverter area is 1 in some unit, right, and delay is 4 in some arbitrary unit, and power is again is 5 in some arbitrary unit, right. And in the same unit, the area for the NAND 1 is 4, for NAND 1 LP is 5, and AND 1 is 8, and so on, right. Let us assume that these PPA numbers for the cells in the library is given to us, right. Now, let us understand that how this net list in terms of generic logic gates, it will be mapped to the cells in the technology library. Now, for given this unmapped net list, one of the solution that can be produced is shown here, right. So, what a mapper can do is that it can instantiate these cells, this NAND gate, right, NAND 1 and this inverter, and implement the same functionality which is delivered by the unmapped netlist. So, first let us check that whether this netlist which is shown which is mapped, whether it is functionally equivalent to the given unmapped netlist. So, for the given unmapped netlist, we have seen that the function y is equal to a dot b plus c whole complement, right. Now, for this netlist, for the mapped netlist, let us compute that what function it delivers, right. So, we can write y is equal to a dot b whole complement, because this is a NAND gate, right, and then it is taking a product with C complement, right, because C is there and there is a inverter. So, this signal is C complement, right. So, this signal will be A dot B whole complement into C complement and then whole complement, right, and then again we complement it because there is another inverter at the output, right. Now, since there are 2 inverters, one inverter here and the other bubble here, right. So, this corresponds to 2 inverter. So, NOT of NOT is the same signal, right. So, we can remove these 2 complement operator, and we can just simply write y is equal to a dot b whole complement dot c complement, right. Now, are these 2 equivalent? So, to establish this their equivalence, we have to invoke the De Morgan's law. Now, you might be aware of this formula, right, x plus y whole complement is equal to x complement dot Y complement, right. This is from the De Morgan's theorem, right. So, now if we look into this part, this is similar to this, right, where x is same as A dot B, right, x is same as A dot B and y is same as C, right. And therefore, we can write this as A dot B plus C, like, or if we use the LHS of this, A plus A dot B plus C whole complement, right. And this is the nothing but the given function which was here, right. So, from this analysis we can establish that the functionality delivered by the unmapped netlist and the mapped netlist both are same, right. Now, let us also evaluate the PPA numbers for the mapped netlist, right. So, for example, what is the area of this netlist, mapped netlist, right. So, in this case the area of NAND 1 is 4, right, and for the inverter the area is 1. So, 4 plus 4 plus 1 plus 1 is equal to 10, right. So, 10 is the area of this mapped netlist. And then we what is the delay, right. Now, delay, assume that the signal is coming at ABC at say 0 time instant, right. So, what will be the arrival time of the signal at Y, right. So, there are 3 paths, the signal can arrive from this path, it can arrive from this path and the third path, right. So, from A and B, what will be the delay, right. If we look into the delay, then the delay of NAND 1 is 8, right, 8, and delay of this again is 8 and the inverter is 4. So, 8 plus 8, 16 plus 4, 20. So, that is for path from A to Y and B to Y, that will be the same and it will be 20 units. And what will be the delay from C to Y? The delay will be of inverter is 4 and this one is in NAND gate it is 8 and for the other inverter it is again 4. So, 8 plus 4 12 plus 4 60. So, the delay, so the arrival time of the signal Y through C will be 60, right. So, in a circuit the worst case delay matters, right. So, if we consider the worst case arrival time, in this case it will be 20, right. And then we can also evaluate the power numbers. Now, it is given that the power consumed by NAND 1 is say 20, right, 20 and for the inverter it is 5, right. So, 5 and 5. So, the total power is 20 plus 20 40 plus 10, that is 50, right. So, these are the PPA numbers, right. Now, this is one of the solutions that the mapper can produce. Let us look at another solution that can be produced for the same problem. So, in this case we are using a NAND gate and then followed by an AND gate, right. So, now we have to first check whether it is functionally equivalent to the given function, right. So, we can write for the map netlist, we can write Y is equal to A dot P whole complement, right, because of this NAND gate, and then we take the AND of C bar or C complement, right, that is Y, right. And again if we invoke the De Morgan's law, then we can easily write it as A dot B plus C whole complement, which is nothing but the given function, right, in these two are equivalent, right. So, the mapped netlist is still producing the same function, right, or it is producing the same or it is implementing the same function as the given netlist, right, and therefore, this mapping solution is correct, in functionally correct. Now, let us also compute the PPA numbers for this circuit. Now, for this circuit, what will be the area? This has got an area of 4, this AND gate has got an area of 8, right, and this inverter has got an area of 1. So, 8 plus 4 12 plus 1 13, 13 is the area. and what is the arrival time, worst case delay or arrival time, right. So, the delay from A to Y or B to Y both are same, and that will be the sum of the delay of this AND gate is 9 and delay of NAND 1 is 8. So, 8 plus 9 is 17. And what about the other path from C to Y? It is delay is 4, right, plus 9 plus 4 is 30, right. But what will matter is the worst case, and worst case delay is 70, right. Now, what about the power number? So, for the NAND gate the power is 20, right. For the AND gate the power is 30, and for the inverter the power is 5, right. So, we have the power as 55, right. Now, these are we saw two possible solutions, right. There could be other solutions also. Let us look into a third solution, right. Now, in the third solution the solution that was similar to what we had as the first solution. Only thing is that now we are using NAND 1 LP rather than NAND. Now, functionally NAND 1 and NAND 1 LP both are delivering the same function, that is NAND, right. But NAND 1 LP has low power, but higher delay, right. This is typical for a high VT transit or as logic cells which is implemented in terms of high VT transistor, right. Now, the functional equivalence is or we have already established the functional equivalence for NAND 1, right. So, if we replace with NAND 1 LP, it will still be functionally equivalent, right. So, we need not worry about the functional equivalence of this mapped netlist, right. But let us compute the PPA numbers for this mapped netlist. So, for NAND 1 LP the area is 5, right. So, this has got an area of 5 and inverter has got an area of 1, right. So, the area is 12, right. Now, what about the delay? So, the worst path or the maximum delay will be in this path, right. And what is the delay? Delay is 12 for this, right. And then we have a delay of 12 for this also, and delay of 4 for this inverter and 4 of this inverter. So, from A to Y the delay is 12 plus 12 24 plus 4 20, and from C to Y the delay is 12 plus 4 16 plus 4 20, right. And what about the power numbers? For the NAND 1 LP the power is 6, and for inverter the power is 5, right. So, 5 and 5. So, the total power is 12 plus 10, that is 22, right. So, we have seen that a given unmapped netlist like this and a given technology library or the cells in the technology libraries, there can be multiple solutions which will yield functionally equivalent results, right. But their QR will be varying. So, to get a sense of what are the PPA numbers for 3 different implementation, let us see a summary of this, right. For the first implementation, we see that the area is 10, delay is 20 and power is 50. Similarly, I have tabulated the PPA numbers for all the 3 solutions. Now, what we see is that the solution 1 delivers the minimum area, right. Out of these 3 solutions, the solution 1 gives us the minimum area, right. And what about the delay? For if we look into the delay, we see that solution 2 is giving us the minimum delay, right. And if we look into the power numbers, then we see that the solution 3 is delivering us the power number, minimum power number, right. So, what this example illustrates is that for a unmapped netlist or a netlist which is implemented in terms of generic logic gates, there could be multiple solutions which will be functionally equivalent, but their PPA will be varying. So, the task of the mapper is to choose a mapping solution or produce a mapping solution which meets its objective, meaning that whether it is trying to minimize area, whether it is trying to minimize delay, or whether it is trying to minimize power. So, this example basically illustrates the opportunities and the challenges of technology mapping. Now, let us briefly discuss how technology mapping is done. There are typically two types of approaches for technology mapping. The first one is structural mapping. In structural mapping, what is done is that suppose there is a portion of a circuit of the unmapped netlist, then this portion of the netlist is matched or compared with the various library cells, and this matching or comparison is done structurally. To match this portion of a circuit with the cells in the library, what needs to be done is that both this portion of the netlist and the libraries or the cells in the libraries both are represented using some base functions, and that base function can be NAND gate and an inverter, or there could be other types of base functions which could be used by the technology mapper. Once the portion of the netlist and the library cells or the cells in the libraries both are represented in terms of, say, these base functions, 2 input NAND gates and inverter, and suitable matches are found for each portion of our netlist, and later on a min cost curve is found among the subset of the matches, right. So, that is what is done in structural mapping. Now, a given Boolean function can be represented in many ways structurally. For example, suppose there is a 4 input AND gate, right. We can represent in terms of, say, 2 input AND gate like this, right. This is one structural representation of a 4 input AND gate in terms of 2 input AND gates. Other representation can be right. So, for the same logic function, the structural it can be represented in a form of or it can be represented structurally in many ways, and therefore, structural mapping needs to consider this, and therefore, some of the matches which could be possible, those are missed by structural mapping, and that problem is solved using Boolean mapping. So, in Boolean mapping, what is done is that the functional equivalence of the portion of the netlist and the library cells, those are actually compared using Boolean methods. For example, both can be represented using, say, BDD, and we have seen earlier that the BDDs are canonical, and therefore, the equivalence of two functions can be tested very easily, right. So, if we use the Boolean method, then then some of the problems of the structural mapping can be solved, and therefore, these days Boolean mapping is preferred, right. Now, the exact algorithms or rather the algorithmic description of technology mapping is outside the scope of this course. So, we will not be discussing these things further. However, if you want to know more detail of technology mapping, I will suggest that you can go to these references. So, let me summarize that what we have done in this lecture. So, in this lecture we briefly discussed technology mapping. So, we discussed that what inputs are given to the technology mapper and what output it produces, And we also discussed that what are the opportunities in terms of PPA and the challenges of a technology mapper. In the next lecture, we will be discussing timing driven optimization. Thank you very much.